Welcome. We will do our final example of determining concavity of an explicit function. This time, for variety, we will do a function with logarithm in it. It's ln of x over x. The differentiation takes a little bit of thinking, so I will give a little bit more detail. Since I have a fraction, I'm going to use the quotient rule. The numerator of function I'm differentiating is ln x, the denominator is x. So in the quotient rule, the first term will be x times derivative of ln x, that's x times 1 over x, minus ln x times 1, the derivative of x, over the quantity x squared. 1 over x times x is 1, so I get 1 minus ln x over x squared. I'm going to use the quotient rule again to differentiate. So I have derivative of 1 minus ln x, that's 0 minus 1 over x times x squared, minus 1 minus ln x times 2x, derivative of x squared, divided by x squared quantity squared. I'm going to simplify this in order to do this sign chart. The next few steps can be done in different orders. It doesn't really matter in which order you do that. Let's simplify each of the terms. X squared times negative 1 over x is negative x. Then if I distribute the 2x in the second part of the numerator, I get minus 2x plus 2x ln x. Now I'm going to factor out an x to simplify the fraction and then also combine the like terms. Negative 1 minus 2 is negative 3, and x over x power 4 is just 1 over x cubed. We can cancel an x. So finally we get negative 3 plus 2 ln x over x cubed. This is 0 when 2 ln x equals 3, and I have to solve that. So ln x is 3 halves, and we take exponentials to get x by itself. So to get rid of ln, you take the exponential. To put it in somewhat incorrect but more understandable terms, take ln to the other side, becomes an exponential. So I get x equals e power 3 halves. Now I'm going to do the sign chart. When you have logarithms, you need to be careful because the domain of logarithm consists of all positive numbers. Ln x is defined only when x is positive. In other words, the domain of a given function is 0 to infinity. So we should start the sign chart at 0, not at negative infinity. Note that if x is positive, then I can always divide by x. So we don't really have to worry about the function being undefined because the denominator is 0. It will be undefined already because ln of 0 is not defined. So we start at 0. We go to the first number where y double prime is 0, that's e to the power 3 halves. Of course, there is no other number where y double prime is 0 or undefined. So we go from e to the 3 halves all the way to infinity for the second interval. The first interval I can pick 1 as my test value. Second interval I'm going to pick e squared because ln is a whole number. Ln of e squared is just 2. Ln of 1 is 0, so if I plug in 1 for x in y double prime, I get negative 3, that's negative. If I plug in e squared, ln of e squared is 2, so the numerator is 2 times 2 minus 3, which is 1, divided by some power of e. Any power of e is positive, which means its reciprocal is also positive. So y double prime is negative in the first interval, positive in the second interval. The problem asked me to find the intervals in which the function is, the original function, ln x over x is concave up. That is when the second derivative is positive, that's in the interval e power 3 halves to infinity. So that's where the original function is concave up.